Deep space sits at a frigid 2.7 Kelvin, but to operate a superconducting transmon qubit, you have to push the temperature down to between 10 and 20 millikelvin. That is roughly 150 times colder than the cosmic microwave background. Right now, the only way to maintain that extreme chill continuously is with a dilution refrigerator. These machines exploit the unique thermodynamic properties of a liquid mixture of helium-3 and helium-4. By constantly pumping the rare and expensive helium-3 isotope across a phase boundary, they create an endless cooling loop. This setup works perfectly well for today's lab prototypes, which typically house a few hundred physical qubits. A fault-tolerant quantum computer, however, will require millions of these delicate circuits working in tandem to solve real-world problems. When you try to scale up to that million-qubit threshold, the physics of our current cryogenic infrastructure simply breaks down. The problem starts with control. Every single qubit requires a dedicated physical metal coaxial cable. These wires carry the precise microwave pulses needed to write and read information to the chip. But here is the inescapable paradox of thermodynamics. A copper or stainless steel cable is a natural thermal conductor. Every time you send a data signal down that wire from room temperature to the freezing stage, ambient heat travels right alongside it. The thermal leakage from a single wire is tiny, but when you multiply that leakage by the millions of coaxial lines required for a fault-tolerant system, the math quickly becomes impossible. Route a million control lines into a single fridge, and the heat traveling down the metal will instantly overpower the system, destroying the delicate sub-Kelvin environment long before the first calculation runs. You might assume the solution is just to build a larger refrigerator. But quantum cooling is governed by a strict physical reality called the Carnot coefficient of performance. This principle dictates the amount of work required to move thermal energy out of a cryogenic environment. As your target temperature approaches absolute zero, that required work explodes exponentially. To extract a single watt of heat from a 15 millikelvin stage, you have to draw roughly 100,000 watts of standard electricity at the wall. Because of this steep thermodynamic tax, standard research-grade cryostats do not offer watts of cooling power. At their base stage, they give you tens of microscopic microwatts. To cool a monolithic million-qubit processor using these current methods, you wouldn't be building a piece of laboratory equipment. You would have to construct a specialized facility the size of a commercial skyscraper or an industrial chemical plant. Reaching fault-tolerant scale is impossible without breaking the strict thermodynamic limitations of current refrigeration geometries. One major architectural workaround is called cryo-CMOS. Instead of running a million cables from room temperature, engineers try to place the active control electronics directly inside the cold environment, sitting right next to the qubits. But active electronics, much like high-speed optical lasers, generate their own localized heat while operating. By cutting down the physical cables, you save space and reduce the passive heat conduction from the outside room, but you immediately replace it with hundreds of milliwatts of active thermal radiation inside the chamber, completely blowing past the tiny microwatt cooling budget. Managing quantum heat loads is a game of cryogenic whack-a-mole. Every time you invent a new way to transfer data, you introduce a new thermal crisis that the hardware cannot absorb. The most promising alternative to the dilution fridge is continuous adiabatic dimagnetization refrigeration, or CADR. Instead of relying on a rare liquid helium isotope, this system uses magnetic crystals to generate its cooling power. Historically, magnetic cooling was a single-shot technology. A strong magnetic field forces the spins inside a crystal to align, shedding heat. When the field drops, the spins randomize and absorb heat, cooling the environment. But once that entropy budget is exhausted, the system has to warm back up to recharge. To make this viable for computing, modern engineering companies are chaining multiple magnetic stages together. While one stage provides cooling, the other recharges, creating an uninterrupted continuous thermal loop. But scaling this engine introduces a massive hurdle. CADR cycles rely on intense magnetic fields, sometimes up to 4 Tesla, and stray magnetic fields are notoriously hostile to superconducting qubits, causing them to lose their fragile state. For magnetic cooling to save the quantum roadmap, engineers will have to heavily shield and isolate the processor from the exact machine keeping it cold. These combined thermal and spatial bottlenecks are forcing an industry-wide pivot. We have reached the limits of the monolithic cryostat, the traditional setup where the cooling engine, the dense wiring, and the processor all fight for the same cramped volume. The industry is moving toward modular designs, like the proposed X-type architecture. This physically decouples the cooling infrastructure from the quantum setup. You build dedicated modules that purely generate thermal power and pipe that chilling capacity into a separate chamber housing the logic. Survival in the quantum race requires abandoning the concept of a single magic fridge in favor of massive, decentralized cooling networks. Public attention usually gravitates toward breaking qubit count records, but those numbers represent only the visible portion of a massive cryogenic engineering challenge. Reaching commercial scale requires conquering the classical thermodynamics of the surrounding facility, a barrier as unyielding as the quantum mechanics on the sun itself. A moment of finality. The team that builds the most effective deep freeze will ultimately be the one that operates the most powerful quantum brain.